Today we shall discuss about the graph of the diffraction in the Fraunhofer diffraction pattern. In Fraunhofer diffraction, draw the graph of intensity of light on screen versus diffraction angle and write the characteristic of this graph. Now see, the central maximum has maximum intensity. In Fraunhofer diffraction, the graph of intensity of light on screen versus diffraction angle is given here in this particular figure. Now see, all minima have zero light intensity. So here wherever there is zero light intensity, there is minima. These are the point of minima. This is your central maximum where you have the maximum intensity of light. Okay. The intensity of maxima decreases with increase in the angle of diffraction. So you can see as you are going away from the central line, the intensity gradually reduces. So as angle theta increases, what happens? Intensity is reducing. As ratio lambda upon A is small, the diffraction will be less, and it is large, the diffraction will be more. Okay, so if you have lambda upon A, diffraction will be less, lambda upon A is more, then diffraction will be more. The angular width of central maxima is inversely proportional to the width of slit. More the width, less the central maxima, or we can say width of central maxima will be less. Okay, and if you have very small width, then the angular width of central maxima will be more. Okay. Now there is a difference between the interference and diffraction. See, it is obtained due to superposition of waves from different coherent sources. Thus, it is the effect produced due to superposition of different wave fronts. So, it is a superposition of different wave fronts, that is interference, while this diffraction, it is obtained due to superposition of waves originated from the different parts of the same wavefront. Okay. The bright and dark interference fringes are equal width. Here diffraction fringes are not of the same width. Central maxima is having the largest width, while width of maxima and minima decreases for the higher order diffraction. Okay. All bright fringes have equal intensities. Here central maximum has highest intensity and it decreases, rather intensity decreases with higher order diffraction. Okay. Dark interference fringes are completely dark here in this interference, while regions of minimum intensities may not be perfectly dark in the diffraction pattern. Now the diffraction occurring because of the two slit. Okay, this is the figure for the diffraction which is produced by the two slits. In the figure, the actual double slit interference pattern, the envelope shows the single slit diffraction. In the double slit experiment, the pattern on the screen is a superposition of single slit diffraction from each slit and the double slit interference pattern. Try to understand both the slits which are there in the interference behave as single slit individually and they produce the diffraction pattern. This is shown in this figure. Figure shows a broader diffraction peak in which there appear several fringes of smaller width due to double slit interference. The number of interference fringes occurring in the broad diffraction peak depends on the ratio lambda upon A. So lambda upon A is the ratio on which these peaks are depending. Okay, that is the ratio of the distance between the two slits to the width of the slit D, that is D upon A. Okay, in the limit of becoming very small, the diffraction pattern will become very flat. And to obtain interference pattern, diffraction phenomena does not need to happen. But to obtain diffraction, we have to have the interference. Okay. Now we have obtained the formula for angular width and linear width of central maxima. Now see, this is the figure in which the central maxima is spreaded, or rather it is spread on both the side of this central line. Okay, and the angle on both the side is made, that is theta here and theta on the other side. Okay, and this with the width, that is beta 0. Suppose width of the slit is a, and that is very small. Okay, in the order of millimeter, and the distance between the slit and the screen is capital D, that is of the order of meter, and this is shown in this figure. For minimum of the side of the central maximum on the screen, theta is equal to lambda upon a. This is known to us, where theta is the half the width of angular width of the central maxima. So angular width will be 2 times theta, that will be 2 lambda upon a. Okay, so this 2 theta becomes 2 lambda upon a. Now arc upon radius is nothing but the angle theta. So arc is beta 0, radius is d. You can see here, okay, that is 2 theta, that is angle is equal to arc, that is beta 0 upon radius, means this distance, that is capital D. According to this, 2 theta will be arc beta 0 upon radius, that is capital D. So beta 0 will be D into 2 theta, and that will become 2d lambda upon a, as theta is lambda upon a. Now angle of n plus 1th order minima, that is beta 0, is the width of linear central maximum. It is minimum distance between the central maximum distance, or we can say the distance between two minima, that is first minima. If you try to understand, these are the two minimums, and distance between these two minimum will give you the width of central maximum. This way also it can be understood. Now linear width of second maxima, that is the angular width of n, means the least angular difference in n and n plus 1. That is the angle of least angle, or rather the angle of least angular in n, or that is theta n, will be n lambda upon a, and for n plus 1th order it will be n plus 1 lambda upon a. Okay, this is a. So theta n plus 1 minus theta n will be n plus 1 lambda upon a, n lambda upon a, so it becomes lambda upon a. The linear width of nth secondary maximum, that is angular width, multiplied by d, so it becomes lambda d upon a. Okay, and beta 0 upon beta, if you take, then that will be equal to 2, or we can say beta 0, that is the linear width of the central maximum is double the width of the other second maxima, that is beta 0 is equal to 2 times beta. Okay, now we shall talk about the polarization, and first of all we shall talk about the polarized light and unpolarized light. Now see, light is electromagnetic wave, and in the oscillation of E vectors, that is electric field vectors, okay, are in all direction in plane perpendicular to the direction of propagation. So if you consider a beam of light, okay, then in this beam of light electric field vectors are oscillating in all the directions. Okay, and this kind of light is called the unpolarized light, and this is the representation of unpolarized light. Now if you have a light in which the light vectors are in one particular direction, they are oscillating in one particular direction which is parallel to each other. Say for example, this is the beam of light and the electric field vectors are oscillating in one particular direction. Then this kind of light is called the polarized light. Here the polarized beam of light is shown in the figure. Now polarized light can be obtained with the help of some of the crystal. Tourmaline is the name of one naturally obtained crystal through which the polarized light is obtained. Say for example, this is the tourmaline plate or the crystal of tourmaline, and there are optic axes. Say this is the optic axis. Now if you pass the unpolarized light through this kind of tourmaline plate, then the light which is emerging out will have only electric field vector which are oscillating in the direction parallel to the optic axis. So the light which you are getting as output, this light is a plain polarized light in which electric field vectors are oscillating parallel to the optic axis. Okay. So this can be understood this way also. If you place this tourmaline plate in the in the where the unpolarized light is propagating, then this light is having the E vectors in all the directions. Now when this light falls on the tourmaline plate, then the E vectors which are parallel to the optic axis will come out, okay, and other all E vectors which are there, then the component of those E vectors in the direction of the optic axis will come out, other all the E vectors are absorbed. So here the light which you are getting is having the oscillation of electric field vector in one particular direction, and this light is a polarized light. Okay. Now using this concept we have the Malus law. Here see, this is the polarized light, this is the polarizer, and this is its optic axis. Now this unpolarized light is incident on this polarizer. Then these are the E vectors which are coming out from the polarizer, okay, which is a tourmaline plate, say for example, and this light which we are getting is a polarized light. Okay. Now one another polarizer is kept in the path of this polarized light. Then what will happen? This is the vector E which is falling on the Polaroid, rather it behaves as an analyzer. Okay. So this is the E vector which is in this particular direction, and now new Polaroid is kept in this way where this E vector is having an angle say theta with its optic axis. So only E cos theta component, try to understand, E cos theta component will come out from this optic axis. Okay, so if you try to understand the intensity of light which is coming out from the first tourmaline plate, okay, the first tourmaline plate, say the E vector which is coming out is having its amplitude to be say E0. Then as you know that intensity initially I0 is proportional to square of amplitude, so it becomes E0 square. Okay. Now when this E0 is falling on this particular optic axis, which is making an angle theta with this direction of its oscillation, then here E0 cos theta component will only come out. So now new intensity I will be proportional to E0 square cos square theta 0. Okay, so what will happen? We have this intensity, that is initial intensity. If I show it by I0, then it will be E0 square, rather it is E0 square. Okay, I0 is proportional to E0 square, and the intensity which is coming out from the second tourmaline plate is proportional to E0 square cos square theta. And if you take the ratio of this, okay, then this E0 square will be cancelled out. So intensity I, if you make as a subject of formula I, will be equal to I0 cos square theta, which is known as the Malus law. Okay, thank you very much.